Good morning everyone and welcome to this Cryo-EM lectures. So, last class we discussed about what is the electromagnetic lens and how we are getting that electromagnetic lens and how when the current is passing through that why there is a motion, but we did not discuss about the what kind of motion we can see for that electron. Most of the time whenever we are discussing about the light microscope, we always telling that okay, if there is a object is if we keep object in a particular position, we can get an inverted image. So, here also do we get a similar kind of inverted image or is there any rotation? What is the trajectory of the electron when electron is going through that electromagnetic field. So, if you remember last class we are discussing about this schematic diagram where we already discussed that okay, this is the bore area and electromagnetic flux is coming from this region which is regulating this incoming electron beam. And now if you look at this electron beam, whatever is going through the center, there is no deviation. So, this electromagnetic field will be almost uniform and then there will be no changes of this path, but deflection will be more whatever is going away from the optical axis, and whatever rays is far away from the optical axis they will feel more deviation and finally they will converge in a one particular point. But this is a simple ray diagram. What about when electron is going inside this magnetic field, is it following a straight line all the time or is there any different type of trajectory is there for this incoming electron? Let us take a look. First let us understand one simple idea. So, here if you remember right hand thumb rule, you can see this is that we all know that in school physics we studies these things. So, right hand thumb rule, if you just consider that okay, your magnetic field is this one and electron is traveling through this, and always there will be a deflection for the electron in this particular direction. So, it will follow this thumb, right. So, this is the magnetic field, this is the electron is traveling through this finger and then there will be a deflection. Another possibility is this, if we just consider that okay, so our direction of current is going this direction, your magnetic field is coming in this way and then deflection of this electron it will be in this direction. So, if we understand this principle, that this will really help us to understand the trajectory, how it is moving so what is the trajectory of the incoming electron. So, you remember that this is the electron is going through this and this is the direction of the magnetic field and this will be the direction of the force, it will deviate in this direction. So, now if you just consider that electromagnetic lens, if we have this kind of electromagnetic lens, what we have? We have a magnetic field in this way. So, this is one is south pole and another one is north pole and this circularly this magnetic field it will go and a electron is coming inside that. So, when there is a magnetic field is going in this direction. So, if you just consider that okay, this is the magnetic field in this direction and electron is trying to enter in this. So, it is not following always 0 or 90 degree, there is a certain angle, and whenever electron will come out from the electron gun there will be all the angles it is going to satisfy, that is the alpha. I was telling that solid angle. So, in all the angles the electron beam it will come, and when it will enter this magnetic field, if this is the magnetic field and it is trying to enter, then definitely it will not go straight anymore inside that magnetic field. It will just started rotating in a different direction. If this is your magnetic field and electron, if this is my magnetic field it is coming and electron is moving in this direction, it will face some kind of force in this direction, and then it will start rotating. When it will start rotating one particular point, in the second point it will feel again another pressure. So that is how it will form a spiral. So electron is coming in, this is the magnetic field, electron is coming this direction and it will start rotating. So it will not follow a very straight line and give an image. So now question it will come that then why are you drawing everything using the straight line? Because we are using the straight line, it is called the ray diagram, and ray diagram is much easier to explain how image formation is happening or how rays are traveling through our microscope. If we just follow this spiral motion of the electron, your ray diagram will be very too many lines will be there and it will be very difficult to explain your ray diagram properly. Now come back to this PPT and see what we are looking here. So here this is a magnet that I discussed. So here this is the magnet and those are the copper wire. So which is winded up tightly, and now there is a magnetic field. There is a one magnetic field is traveling in this direction and another magnetic field is traveling in this direction. Okay, and this is the right hand thumb rule what I already discussed. Now a electron is going through this axis. As I mentioned previously in previous slide that if electron is traveling through this axis, there will be no deviation of that electron, because if you look at this one, the magnetic field, one magnetic field is going this direction and the other one is traveling in this direction, and here the magnetic field is almost 0, there is no magnetic field. So this electron whatever going through the optical axis, there will be not too much deviation. But what about if you think about that, okay, a electric current, it is an incoming electron is going through this path initially. So there is a angle difference between this particular electron and this particular electron, and when it entered this magnetic field, so the magnetic field is going this particular direction, right? So magnetic field is going in this direction and electron is trying to enter. Now if you follow my hand, what you can see, this is an electron. So this is the electron, it is trying to go, and this is the magnetic field, this is the magnetic field. Now when electron will enter here, the magnetic field is creating a pressure in this direction and it is deviating the path of the electron in this particular direction. So exactly if you go to this diagram, you can see this. So there is a motion of this electron there is a change of the motion of this electron in this particular direction. When it is somewhere here, it will face again this kind of particular motion that okay, electron is pushing in this direction, and finally you can see it entered to the another magnetic field which is going through this cycle. When it will enter, it will feel the opposite force and it will start deviating from its actual path. So now if you follow this one, we can see a spiral movement of this electron. Now how many spiral will be there inside this electromagnetic lens, that is depending on what kind of magnetic field we are using, how strong is our magnetic field. If our magnetic field is very strong, definitely will be a much more spiral motion. Now this is the electron trajectory. If I ask you guys to draw a trajectory of the electron when electron is traveling through a electromagnetic field, so that is the trajectory we have to draw. Next, okay, so this is a real scenario that here this is our electromagnetic lens and this is the cross section of both the lens, where you can see those are the individual copper wire which is winding the soft iron, and this is the gap between this and this is the bore area where the electromagnetic field is coming out and which is interacting with our incoming electron beam. So now this is an object and electron beam is coming. When it is entering into this magnetic field, there is a deviation. So in one particular ray you can see one ray, it is coming in this particular direction, they come together and converge and form a crossover here, and then this particular electron beam is interacting with the image plane here. In the other side, one ray, it is coming in this particular direction and they come in this direction. So here there is a deviation you can follow. If you just follow this path, there is a deviation and it is coming and forming an image here. So this is actual image plane. So rays are not coming and directly interacting like that and forming a straight image. So if I just draw this one, it will be easier for you. So in normal case, whenever we are doing a ray diagram, what we do, generally we follow this way and then we tell, okay, this is our image. But actually you can see that path is different, it is not following the same path. Here you can see there is some deviation here. So one, it is that beam is deviated like this one, and there is another beam it is coming. So now based on this deviation, one is coming here and another one is coming here, and then it is giving us an image which is basically like that. So if you remember our light microscopy, if you just consider any glass lens, what we are getting. So if this is a glass lens and if we have a object at 2f distance or in between f and 2f distance, rays will come here and one, it will go through the center and it will form an image always like that, right? So we are always telling that there is a, so if my object is staying in between f or 2f distance, so it will form a real image and inverted image. Here also it will form an real image, but there will be a rotation, it will be not completely inverted image all the time. Based on our magnetic field, based on our what kind of magnetic field we are using, that deviation it will depend. And always remember that rays are always following a spiral motion, it is a helical motion, it will be not a straight line. Okay, so that we are discussing that, okay, even if we are considering that there will be a motion, what kind of that motion will be? Will it be a only one spiral motion? This is the optical axis we are talking about that. Okay, so here if you look at, so our optical axis is this one. Any rays, if it will go through this one, there will be no deviation. But if there is a magnetic field, so magnetic field cannot be stopped suddenly here, it is depending on what kind of lens we are using and what is the magnetic field, and it is going to affect. An electron is traveling to this magnetic field and we can see a spiral motion from beginning when it will start entering. So it is not like that the previous diagram, there will be only one spiral motion like this and it will go out. So there will be a multiple spiral motion, it is possible, it is depending on the magnetic field. So here you can see this copper winding. So here our copper winding, all this part it will be here, and this is the area where water flow will be there, which will try to keep this lens system in a proper temperature. So it will help us to image in a correct way. So there should not be too much deviation. So now I hope you understand that why we have to maintain the temperature of that particular lens, because if we don't maintain the temperature of a particular lens, what is going to happen? It will change the magnetic field. If it will change the magnetic field, it is going to change the spiral motion of the incoming electron beam, and their converging and diverging property it is going to change, and that is going to change our magnification, that is going to change our focus. and that is the reason it will be always better to maintain the temperature of the electromagnetic lens, so there is not too much changes. Old days, if you just consider the 10 years ago or 15 years ago, generally we are keeping electron microscope in a very dark room. That time we are using CCD camera and inside that dark room it is not allowed that when we are doing actual imaging, people will go in and out all the time, because if people will go in and out inside the microscope room, there will be a vibration that is going to affect our imaging. And also there will be, if there is a too much temperature changes, that is going to affect our electromagnetic lens systems also. That is the reason it is always better to maintain the temperature, and during imaging we should not go in and out all the time. So, and the second option is that always maintain a proper temperature for the microscope. In any microscope facility, if you visit, you can see that there will be a temperature is always maintained. It does not matter if it is a winter or rainy season or summer, we are always trying to maintain a certain temperature. That is basically trying to keep the environment in such a way that there is not too much temperature fluctuation, as well as there will be a chiller system which will maintain the temperature of this lens. That will help us to get the very stable magnetic field and which is going to affect our focus, magnification and intensity and other properties also. Now, this is the lens system we are talking about last class also, that different types of lens. So, in this particular different types of lens, I discuss about that objective lens. So, here we can see there is a objective lens we are talking. In last class also I discuss about this objective lens. Objective lens, there is a split pole piece. So, when I draw last class, you can if you remember that I mentioned that okay, if there is a objective lens is like that, so it will be connected like this. So, here also you can see there is a two objective lens which is splitted. So, here there is a gap between these two objective lens and your sample will stay somewhere here, and this is basically when there is a not a single objective lens. When this objective lens is splitted into halves, there will be a gap between those two lenses, and which is helping us in many different way, and that is one of the most important part when we will decide about to think about a microscope, about the biological sample purposes or material science sample purposes. So, here if you go through this, we can see that compared to other lenses in TEM, the objective lens is a very strong lens, because objective lens and last condenser lens together we have to converge the beam very strongly. So, here you can see the objective lens mentioned as a very strong, and if you look at here the objective lens overall magnetic field, if you just consider roughly it is 2 Tesla. So, if we just consider that objective lens, there is a the objective lens is splitted into two halves. It is a most flexible objective lens is that in which the upper and lower pole pieces are separated. So, here you can see the upper and lower pole pieces are separated, and there is a gap, because if you remember when I draw that column diagram, I mentioned that your sample will stay inside that objective lens. So, there will be upper objective lens and lower objective lens, and your sample will stay inside that. So, for biological sample purposes, many times we have to tilt the specimen. We need certain angle to collect data which will going to cover all 360-degree angle of that sample, and that is basically help us if objective lens is splitted into two halves. If it is not, then that pole piece gap will be so small that tilting is not possible. Mainly that high resolution HR10, this gap is so small, even you cannot tilt. You can just do some normal imaging at very high resolution, but doing some biological work or tilting or cryo holder insertion, those problems will be there, and because of this splitting of this pole pitch, there is lot of other benefits are there that we are going to discuss. Now, if you come, so here that it is a very straightforward to design specimen holder that do a variety of tasks such as that I mentioned, the tilting, rotating, heating, cooling. So, that is the benefit we have when we have a split pole pitch and objective lens. So, this cooling is very important when we are doing the cryo, because we need a cryo when we do the cryo-EM, or we have to maintain a cryo temperature inside in this particular area. So, objective lens is staying near the goniometer. So, that is the reason this is important for the biological term. If you just consider, the most of the time there will be a split pole pieces. So, objective lens will be two halves, one will be upper objective lens and lower objective lens. Sometimes for biological science sample we do tilting, because cryo-electron tomography, sometimes rotating is required. Previously we are collecting data, tilt pair data also. So, those times that rotating, tilting, those is possible if our that objective lens is splitted. Now, this also I discussed in last class that okay, that for the top entry immersion lens, this is the top entry immersion lens. So, the top entry immersion lens, there is a the flexibility is not that much. So, that we already discussed in last class also, that the top entry stage the specimen is surrounded by the objective lens. So, it is a more difficult engineering to manipulate that heating or cooling of the specimen. It is not possible to get the X-ray detector near the specimen also. So, analytical microscope, so this is the kind of microscope we can lens we can use it for that analytical microscope, mainly for the material science purposes, not for the biological science purposes. Now, this is the another lens system that is not required for our purposes. So, our main aim is discussing about the biological term. So, you just remember for the biological term mostly we are using a lens system where the objective lens into split it into two halves. Now, let us go to little bit about the condenser lens system. If you remember that, we can discuss little bit more about the condenser lens system, what this condenser lens system is doing. We already discussed about the objective lens system. In the PPT you will get lot of details, but many of these details are not required for biological science purposes, but if someone is interested they can go through that, okay, how this what kind of magnetic field we are expecting and in objective lens, and what is the material and how we can make a different type of superconducting lens also. So, if you are someone is interested, they can go through those slides. So, now the magnetic field or that magnetic field is very important, because that is the part it is going to regulate the movement of the incoming electron beam. If we just consider there is a two magnetic lens we are showing here. So, here you can see this is the gap and magnetic field is coming out in this path, and now there is an incoming electron, and you can see how they simulated this one to show it what current we magnetic efflux we can expect and what kind of movement we can feel for our incoming electron beam. So, if we just use a very less magnetic field, that is called the weak lens. So, we are using a same electromagnetic lens, just changing the magnetic field, and then we are trying to converge the beam or diverge the beam. So, when we are having a very less magnetic field, this is called the weak lens. When we have a very strong magnetic field, something like that, we can tell that this is a very strong lens. So, here you can see if there is a very weak lens, even if the electron beam is coming in this, so even there is a deviation will be very less. But if we gradually increase the magnetic field, so we are gradually increasing the magnetic field, where you can see that deviation of this electron, it is going to change more and more, because initially when the electrons are coming from this side, there is a not too much magnetic field and overall deviation it will be less. But when we are going very strong magnetic field, that time it is going to deviate the electron beams more. And if there is a deviation in this direction, if you can follow this pathway, same thing is possible in this lens also. So here also one electron beam it will come here, so deviation will be much stronger and they will converge all the beams here. But in this particular case, when magnetic field is very low, they will go all the way and converge at the bottom. Same thing is true for this one. So when we are same magnetic field, same electromagnetic lens, we can use it, very strong magnetic field, and converge the electron beam, and focus point it may move. This crossover point, we can say this is a crossover point. Crossover point can go up and down. So that is basically depending on what kind of magnetic field we are using. So that is one of the major difference between the normal optical lens system and the electromagnetic lens system. The same electromagnetic lens, it is a fixed lens. We cannot change the position of the fixed lens, but we can change the magnetic field. We can change the electric current flow through this lens and change the magnetic flux, and which is helping us to converge the electron beam, and the crossover point can move up and down. That is we are going to discuss more in the next class. So here when we are using a very strong magnetic field, crossover point is going up, we can say that is a strong lens, and otherwise if magnetic field is very low, we can say that is a weak lens. One more thing that I have to discuss little bit, that is about the lens hysteresis. If we just here, you don't have to go through each and every details. So only one thing you remember, that whenever we are working on a soft iron and those it has some kind of magnetic flux, it will stay there. So if we have a lens, we are using a very strong magnetic field, and suddenly same metal we are using a very low magnetic field. In both the cases it cannot behave in a same way. There will be some, if we are using a very strong magnetic field, some of this information stored in this metal ion which will not follow the same pathway and it will not come back to the same position. So that is a problem, and that is basically called the magnetic hysteresis of the lens. So what is that hysteresis of the lens? So here if we just look at, if we just consider that okay, there is a magnetic field V and this is the path what metal is following, and this is the minus hysteresis and this is the plus hysteresis. So if a metal it is following, when we are having a magnetic field, it is changing, it is going through this path and it is saturating after a certain time, and we are going in a different direction and changing the magnetic field. When we are changing the magnetic field, it is not going to follow the same path this way. So when it is going in this direction, it is not going to follow the same, it is not going to follow the same pathway again. So it will follow a new path, and this is the new path it is going to follow, and then it will come to the saturation point here. So this is called the lens hysteresis, that okay, if we are using some kind of magnetic field, some of this information will store in this lens and it will not immediately come back to that normal position. So if this is a plus magnetizing force, this will be a minus magnetizing force. So, H is the magnetizing force in a two different direction, and this is the magnetic field, that what we are talking about, that flux density. So, now this magnetizing force, it will vary between the metal. So, why it is required for our cases? Because we are talking about the strong lens and weak lens. So, weak lens means our magnetic field is very low. So, if we just draw that one, when there is a very low magnetic field, we have a rays coming, and if we just consider this is a magnetic field, and the magnetic field is so low, there is no change. So, rays will come and it will go all over like this. So, it will not converge, it will go and it will converge at the below. Now, we have a same magnetic lens and we have a very strong magnetic field here, and we are trying to converge this electron beam very hard way. So, when the electron beam it will come, and after a certain time, it, because the magnetic field is strong, it will start deviating in this way. So, you can see that in this particular case they formed an image here. In this case, it crossing the image plane and it cannot converge, but here it is converging based on this strong electromagnetic field. Okay, fine. So, strong electromagnetic field, I am using my lens as a very strong electromagnetic field. So, here this is the positive P I am using, and my magnet or soft iron electromagnet is completely saturated. Okay, and then suddenly I want to use the same electromagnetic lens at a very low magnetic field or a different magnetic field, and it has to start from here and come back to this particular position. So, if you look at that magnetizing force, the magnetizing force, when it is going, it is in a different position, when it is coming back. So, these 2 points are different, it has a different type of magnetizing force, and that is going to affect when it is give us a magnetic field here to converge or diverge the electron beam. So, that is the problem, and that is the reason we have to remember about the lens hysteresis also, otherwise it will be a problem. So, these things is very important when we are constantly doing the magnification, because in magnification also we are using some kind of electromagnetic lens, and if we use only the electromagnetic lens, what is going to happen? In presence of this electromagnetic lens, we are using intermediate lens and 2 projector lens, which is helping us to magnify our images, and we are using sometime a very strong magnetic field or weak magnetic field to get a low magnification image. Same lens I am using a very strong magnetic field to go very high magnification. That is the time that lens hysteresis is a problem. So, if we are using a image at a very high magnification, we should not suddenly jump from very high magnification to the low magnification, or if we are working to the low magnification, suddenly within a second we cannot go to the high magnification and do the imaging. We can do the imaging, but it is going to affect our images, and as you know that there will be a change in the magnification because of this magnetic field, that is going to will not give you the exact magnification all the time. So, that is the one of the reason whenever we will report any TEM or cryo data, we should not mention the magnification. We can tell that calibrated magnification is this much, but we should use the scale, that is the distance, and that may vary little bit here and there, but it will be the correct representation of any image. Thank you all for your attention. In the next class, we will discuss more about the ray diagram and how the images is forming. So, we will wait for the next class.